Good afternoon everybody. Today I am going to tell you about the one component systems, in which are included the water system, sulfur system and the carbon dioxide system. But before moving to the one component system, let us see how the degree of freedom varies with the number of phases in one component system. Now, as we all know, according to the Gibbs phase rule, the formula is given by F is equal to C minus P plus 2, where F is the degree of freedom, C is the number of components, P is the number of phases. So, for one component systems, three cases can arise. First is when the number of phases is, when P is 1. Then what will happen? The value of F will be equal to, C is 1 since we are taking the one component system into consideration. So, C will be 1 minus 1 plus 2. This comes out to be 2. This means that the system is bivariant, means that the degree of freedom is 2. This means if we are taking the temperature and the pressure variables into consideration for studying the phase equilibria, then both have to be fixed. Now the other case is, the second case is when P is equal to 2. This means two phases are present. If we talk about the one component system, and if we talk about the water system, the two phases can be liquid or the solid, means water, or ice, it may be ice or the water vapor, or it may be liquid in the water vapor. So when two phases coexist in an equilibrium, so then what will be the degree of freedom? The value of degree of freedom F will be, C is 1 minus P. P is 2 plus 2. So this comes out to be 1. This means that only one variable, when we are taking pressure and the temperature, as we will see we will be taking in the water system, then only one variable needs to be fixed, the other will be automatically fixed, and we say that the system is monovariant, or we can say that the system is univariant at this point when F is equal to 1. Now the third case is when P is equal to 3. This means when three phases coexist in equilibrium in a phase equilibrium system which we are studying. For example, if we are taking water system, then the three phases which can coexist in equilibrium at a certain point can be the ice, means the solid phase, water means the liquid phase, and water vapor means the gaseous phase. These all phases can coexist. Then what will be the degree of freedom? Then the degree of freedom F will be given by C is 1, P is 3 plus 2, and this comes out to be 0. This means that when three phases are present in equilibrium in a one component system, then the degree of freedom is 0. This means that the system is non-variant. We call it as non-variant when the degree of freedom is 0. So we have seen all the three phases. Now we will see the phase diagram for water system, and we will see how the degree of freedom varies with the number of phases present. Now let's come over to this water system diagram. So as we all know that water system is a one component system. It exists in three phases: ice, solid ice, liquid water and the gaseous vapor state. But since all these phases can be represented by a single chemical entity, and that is H2O, so it is a one component system. Now this the effect of temperature, this is the pressure axis and this is the temperature axis. Now the effect of pressure and temperature on various phases and on the equilibrium of the various phases is determined experimentally, and then it is plotted on the pressure and the temperature axis, and what we get is a phase diagram. So actually phase diagram is the representation of the effect of pressure and temperature on various phase equilibria of the system. So this is the phase diagram of water. Now as we all know that this water system can exist in ice, water and vapor. These three phases can coexist at some point. The main equilibria are ice and vapor, water and vapor, and ice and water. These are the main equilibria which exist. Now in this phase diagram, what we see is one curve OA, OC, OB, and there is one this dotted curve OA. Now this curve OA, so this is the salient features of this phase diagrams, mainly these curves. One trigger point you can see where these three curves are meeting, and we can see these areas. Actually these areas are, here we are having, this is the solid area which we can call ice. This is the ice area, this is the vapor area, and this is the liquid area. This is the area for liquid water. By area I mean the area under BOC. This area represents solid ice. The area under OAOC, this area, this represents the liquid state, that is water, and the area below BOA, this area, this represents the conditions of the vapor state, means the gaseous state. So the salient features we can again say that they are the curve OA, OC, OB, areas AOC, AOC, BOC, and area BO below BOA. Moreover, one trigger point. So these are the salient features, and one most very important feature is this metastable curve OA dash. So now let's come to all the curves and areas one by one. First of all, let's take this curve OA. As we all can see, this OA is the vapor pressure curve for liquid water. What we see is that the 1 ATM line cuts it at 100 degrees centigrades. Moreover, it shows the effect of pressure on and temperature on the vapor pressure. Effect of temperature on the vapor pressure of the water. What we see is that as we are increasing the temperature, the vapor pressure increases, and it reaches to this point, which is 374 degrees centigrades, and actually it is the critical temperature. Beyond this temperature, this curve will have only vapor, or you can say it will have some homogeneous phase over there, mainly vapor. So beyond this, the liquid phase will not exist, and only a homogeneous form of critical mixture will exist, and this corresponds to 374 degrees centigrades, which is the critical temperature. This is the critical temperature, and the corresponding pressure, which corresponds to this point A, is actually the critical pressure, which is 218 atmospheres. This is the critical pressure. So the two phases which coexist in equilibrium along curve OA are given by the vapor phase and the liquid phase. So which phases are coexisting here? The liquid phase and the vapor phase. So if we are going to calculate the number of degrees of freedom along this curve OA, what we get is, as we all know that the formula for calculating F is equal to C minus P plus 2. If we have to calculate F, C will be 1, since it is a one component system, so C will be 1 for this curve OA. C will be equal to 1 minus, how many phases are in equilibrium with each other? Two phases. Which two phases? The vapor phase and the liquid phase. So it will be 2 and plus 2, and this comes out to be 1. This means that the system is monovariant along the curve OA, or the degree of freedom is 1. This means that if we fix one variable, the other will be automatically fixed. And this is what we actually see also, because if we take any point on this curve, suppose we take this point on this curve, and if we fix the temperature over here, means if we fix the temperature over here and we take this point, then the pressure will automatically be fixed. We need not to fix the pressure, because if we have fixed the temperature and we have taken this point and we have fixed the temperature, then the pressure is automatically fixed. This means that the system has 1 degree. Now let's come to this curve OB. OB is the sublimation curve. Means along these pressure and temperature conditions, ice changes to vapor state, and there is no involvement of the liquid state over here, and this signifies the sublimation curve, and it is extended up to absolute temperature, that is minus 273 degrees centigrade, and this is actually 0 degrees centigrade, sorry 0.00575 to minus 273 degrees centigrade. So these are the coordinates of OB, and this also shows the effective pressure and temperature of the sublimation of the ice, and the two phases which coexist at this on this curve is given by ice and the vapor state. Similarly, when we are going to calculate the degree of freedom along the curve OB, what we get is F is equal to again 1 minus 2 plus 2. Here the number of phases are ice and the vapor phase. So F will be again equal to 1, that is the system is monovariant along the curve OB, and if we fix the temperature or we fix the pressure, the other variable will be automatically fixed. Now let's see the curve OC. Now we are having the curve OC. It starts at point O and ends at point C, and as we can see, this 1 atmosphere line cuts it at 0 degree centigrade, which is the freezing point of water, and this curve signifies the melting point curve of ice, or we can say the fusion curve, or we can say the freezing point curve of water. And one silent feature of this curve is that it is inclined towards the pressure axis. What does this denote? It denotes that as we increase the pressure, the freezing point is decreasing. Sorry, if we increase the pressure, the freezing point decreases. Suppose we are moving from this point to this, we are selecting this pressure, then the freezing temperature is this much. Okay, but when we increase the pressure to some other level, then the freezing point becomes this. Means that the freezing point is decreasing with the increase of pressure. This is due to the anomalous behavior of water. We all know, because suppose we are taking any gas and we increase the pressure, what happens? The gas will liquefy. This means that if we increase the pressure, then this thing should change to vapor state. But no, here the freezing point is decreasing and it is changing to the liquids. So again, if we calculate F over here on this curve OC, what we get is F will be equal to 1 minus 2 plus 2. Here the two phases in equilibrium are ice and the liquid water. The two phases in equilibrium are ice and liquid. So the degree of freedom comes out to be 1, as we have seen that along the curves the degree of freedom comes out to be 1. That means the system is univariate, or you can say the system is monovariant along the curve. Along this curve also, the melting point curve also. This means if we fix the pressure, the temperature is automatically fixed, or on the other side you can say that if the temperature is fixed, then the pressure is automatically fixed. Now we come over to this. This is a special metastable curve. If we extend this curve to the lower temperature limits, water has a special property that it can be supercooled to a temperature of minus 9 degrees centigrade. If we start here at about 4 degrees centigrade and we go on carefully cooling it, then we can get a supercooled liquid to minus 9 degrees centigrade. But if this equilibrium is slightly disturbed by vigorous shaking or by introduction of a crystal of ice, then immediately the supercooled liquid will change into ice and the equilibrium will be disturbed, and ultimately this OA curve will merge to the OB curve. So this OA curve is the curve for the supercooled liquid, this curve, and it is known as the metastable curve. And the two phases in equilibrium, here also there are two phases in equilibrium. One is the supercooled water and the ice. they are in equilibrium with each other. So this is known as the metastable curve, and this is a peculiar property of the not only water but certain liquids also exhibit this property. Now comes this point O. We see that this curve AO, this is meeting over here OB, and this fusion curve, this also meets at a certain point. This point is known as the triple point, and here all the three phases they coexist. Here we are having the liquid phase, the ice means the solid phase, and the vapor phase. They all coexist at this point, and if we are going to calculate the degree of freedom at this point, what we get is number of components is 1, number of phases, these three phases are coexisting at this point, plus 2, and this comes out as 0. So this means that the system is non-variant at this point. The degree of freedom is 0. This means that we don't have to fix neither the pressure nor the temperature. We don't have to fix it. It is automatically fixed. And the conditions here are, this is 4.56 mm of Hg, pressure is 4.56 mm of Hg, and the temperature is 0.0075 degrees centigrade. However, in some books it is also mentioned 0.0098 degrees centigrade. So these two conditions, pressure and temperature values, are fixed for triple point, and we need not to fix. This is the meaning of the degree of freedom is 0. This means that we don't have to fix neither the pressure nor the temperature, they are automatically fixed. If we are having this much pressure and this much temperature, then definitely the three phases coexist together with each other. Now let's come to the areas. As we have seen, this is VOC. This is the area for the solid state, that is ice over here in the water system. So this we are having this ice. Now let's calculate the degree of freedom for this area. For area BOC, let's calculate the degree of freedom. F. F is equal to C minus P plus 2. What is C? C is number of components, we all know it's 1. P is number of phases. Now how many phases are there? There is only one phase, ice. So it will be 1 plus 2 plus 2. This comes out to be 2. This means that in this area the system is bivariant. This means that we have to fix both the pressure and the temperature in order to define this phase. In order to describe this phase, we have to fix both the pressure and the temperature. And yes, it's true, because if it is a point, then we can locate that this should be the pressure, this should be the temperature, or if it's a line, then we can locate the pressure and the other will be automatically fixed. But for an area, we have to define both the pressure and the temperature. The pressure should be this much and the temperature should be this much for this area. So this is the meaning of being the bivariant system. Similarly, if we talk about this vapor state also for the area AOB, F will again come out with 2, and similarly for this liquid phase also, area AOC, F will come out with 2. So this means that the system is bivariant when we are in any area. Along the lines, the system is univariant, and at the triple point where all the three phases coexist, the system is non-variant, or you can say the degree of freedom is 0. So once again, let me revise the whole this phase diagram. First of all, what is phase diagram? Is the study of the effect of pressure and temperature on the coexistence of various phases. Now this phase diagram of water, and it consists of three curves, OA, OB and OC. This is the vapor pressure curve, shows the effect of pressure and temperature on the vapor pressure of water. And this is the curve OC, it is the melting point curve, and it shows the effect of pressure and temperature on the melting of ice, or fusion of ice, or the freezing point of water. And this is the sublimation curve, and it shows the effect of pressure and temperature on the conversion, sublimation of ice to vapor. Ice changes to vapor, that is the sublimation process. On the sublimation, so this is the sublimation curve. And one is the metastable curve given by OA dash, which is actually the supercooled liquid along with its vapor, and then by very careful cooling of the liquid we can attain this curve. The triple point curve corresponds to 4.56 mm of Fg, this pressure, and 0.0075 degrees centigrades. This OB curve ends at absolute temperature, and here this OA curve ends at the critical temperature and pressure. A is the critical temperature, 374 degrees centigrades for water, and the pressure is critical pressure is given by 218 atmospheres. And here is the curve OC, which is the melting point curve. And the main feature of the water system is that this OC curve means the freezing point curve. It is tilted towards the pressure axis. If we remember the Clausius-Clapeyron equation, it shows that dP upon dt, with the slope of this curve, is actually negative. dP upon dt is negative. This means that the volume of ice is more than the volume of water. And so, as we have studied the mass formula also, as the volume of liquid is less than that of ice, so when it will actually favor the formation of liquid when pressure is increased. When pressure is increased, it will tend to reduce the volume, and ultimately, since the volume of ice is more than that of liquid water, so it will tend to convert to water with increase of pressure. So this curve is tilted towards the pressure axis. So this is all about the water system. Thank you very much.